Okay, this is a topic so important that it's been given a bunch of different names by different communities. We're going to call it weighted nonlinear least squares fitting, but it's also often called chi-square fitting. It's also maximum likelihood estimation of parameters, and if you're a Bayesian, it's also Bayesian parameter estimation, although then it involves the assumption of a uniform prior and maybe some other normality assumptions. We'll talk about this. So all of these different names are almost the same thing. What we're not going to talk about is what happens if you do a Google image search for weighted nonlinear least squares fitting. You get a picture of tight-fitting jeans that are used in square dancing. So here's the setup. We're going to make some measurements of a quantity y, and those measurements are indexed by I, and each yi is a measurement that's made at a certain place or a certain set of coordinates x sub I, and we have a model. The model is a function y of x sub I that tells us what value we expect to measure. Except that that model is not yet complete because it has some unknown parameters in it. So for example, if you imagine that the model is a polynomial and that this polynomial of x is supposed to predict y, then the unknown parameters here might be the coefficients of that polynomial. Now when we measure y, we don't get exactly the value of the model, not for any parameters b, because there's an error term, there's noise in the measurement. And so each yi is corrupted by some error e sub I. And we're going to assume here that the errors are drawn from a normal distribution, so that each error has a standard deviation sigma sub I. We're going to assume we know those. We don't know the actual value that's drawn for each data point. If we did, there wouldn't be any uncertainty as to the value. But we do know the distribution that that error is drawn from. Usually we're going to assume that the errors are all independently, that each I is an independent draw from this normal distribution. But everything we're going to talk about goes through just slightly changed if in fact the whole vector of errors here, corresponding to the whole vector of measurements here, comes from a multivariate normal distribution with some covariance matrix sigma. So in that case, we have to draw the whole vector of errors E in one draw from this multivariate normal distribution. So what's the point of all of this? The point is that we want to find the parameters of the model B from the set of data, the yi's. And then we'll want some other things. We'll want to know how accurate are those parameters, and finally we'll want to know, should we believe this model at all? Now least squares fitting is usually presented in a frequentist language as maximum likelihood estimation, but we can just as well think of it as a perfectly Bayesian thing to be doing here. So let's go through that. We want the probability distribution, a posterior distribution of the parameters B, given the data set of the yi's. And Bayes tells us that that's proportional to the probability of the yi's, given the parameters B, times, as always, some prior. Notice that this is a prior on the parameters, a prior on B. Now what is this probability of the data given the parameters? If you think about it, the only random variables here that are subject to the idea of probability are the errors in the previous slide. Everything else was a known number. We know what the measurements yi are, and if we're given B, we know what the model predicts at any given measurement point x sub I. And if we subtract that 2, we get the error term e sub I, and that's the random variable, and that's what we assumed was normally distributed. So if we take that random variable and divide it by its standard deviation, then this is a t-value, and the normal distribution is e to the minus a half that t-value squared. And we have a product over all the individual data points of this distribution because we assumed that the errors are independently drawn, and therefore the probability of the whole data set is just the product of the probabilities for the individual data points. And as long as we're Bayesian, we still have a prior probability that we're tracking through here. Now the product of a bunch of exponentials is the exponential of a sum of those terms. And if you stare at this for just a second, you'll see this, except for the minus a half, this is exactly our friend the chi-square statistic that we talked about in a previous segment. So we can write the posterior probability of the parameters as proportional to e to the minus a half the chi-squared statistic setting those parameters equal to some value. And then we still have a prior on those parameters, but we're going to get rid of that one soon. So now the idea is find the parameters b, and it's a vector. There are more than one parameter in general. Find the value of b that minimizes this probability. Or if the prior probability is uniform, then this doesn't come in anymore, and we want the value of the parameters b that minimizes the chi-square in this exponential. Now sometimes models are linear. That would be a property of this function y up here. And if y is a linear function of the parameters b, then you can actually find the value b0 that minimizes chi-squared of b just by doing linear equations. They're called the normal equations, or there's a better way of doing this with singular value decomposition. This isn't within the scope of this course, but you can look in any textbook. I'm of course partial to Numerical Recipes, 3rd edition, where it's section 15.4. But that's a very special property of models y, and generally we're going to be more general than that and look at the nonlinear case. And then you simply have a general nonlinear minimization problem over the space in which these parameters b live. And there are various algorithms for doing nonlinear general minimization. None of them are perfect, but many of them are workable, as we'll see. So if the prior on the parameters is a constant, so that this p of b is no longer there, then these parameters have a frequentist name. They're called the maximum likelihood estimate. So maximum likelihood estimate is basically Bayes with a uniform prior. Now I want to make this all a little bit more concrete by taking a particular example that I've jiggered up here. So I want you to pretend that you see in this picture down here only the data points, not these curves that I'll come to later. And these data points are, I think there are 20 of them, they're measurements as a function of x here that seems to go between 1 and 8 or so of some quantity y. And I have a model for these data points, and here's my model with 5 unknown parameters. The unknown parameters are b1, b2, b3, b4, and b5. And if you look at what this model says, it says that we expect y of x to be something like a constant times a dying off exponential, and that's what we're seeing in this high point and these fewer lower points here. And then superposed on that by addition, a Gaussian-shaped lump which has amplitude b3, it has central location b4, and it has standard deviation b5. And you can see that these points that generally rise here and then fall off here are the points that are dominated by the Gaussian piece in the model, whereas the points here at the beginning are the points that are dominated by the falling off exponential piece of the model. So here's our chi-squared statistic again. And we're just going to do the maximum likelihood estimation to find the numerical values of those 5 parameters, b1 through b5. Now, here's a case where we're just going to use MATLAB's built-in nonlinear fitting algorithms. And they're going to work. They'll work the first time. it's key in nonlinear fitting that you have to make a good starting guess for the parameters. And so I'm going to sort of read off starting guesses for these parameters based just on a very rough look at the shape of this curve and an understanding of what the functional form was up here. So I'm going to do this in MATLAB. Here's the anonymous function of the model. Anonymous functions begin with an @ sign. That's basically says that the y that comes out of the model, that's this y right here, is the expression that involves the b 1 through 5s and also involves the x's here. In MATLAB, of course, this x can either be a single value of x, or I can put in a whole vector of x's and get out a whole vector of y's. And I have my chi-square function, this thing up here, and you can see that defining it as an anonymous function only of b, because that's the thing we're going to want to vary around to find the minimum. And then in the definition of the function here, which I'll let you read, you can see that x and y enter, but they just enter as fixed external vectors, and they contain the 20 data point values of x and y that are shown in this picture here. So here's the complete process. I write down a guess of initial parameters. Where did I get this guess? Well, the first two parameters are the height of the exponential and how rapidly it falls off. And you can see I thought the height started at about 1, and it's fallen off pretty fast by the time it gets to 0.5 here, so I'm guessing a value 2. And then from the points in this lump here, I guessed that the lump was centered around 3, so I guessed 3 right here. I guessed that it had an amplitude of about a half. Well, a half is over here, but we're still maybe getting some of this dying exponential here. Anyway, half is a good enough guess. And then I guessed that its standard deviation, maybe from here to here, is 1.5. Anyway, those were my initial guesses. And now you use Mathematica's function fminsearch, which finds a minimum of the chi-square function, this function, as a function of the parameter values here, starting at the guessed values here, I should say, as a function of b, beginning at a beginning guess here. And then I'm going to want to plot the result along some grid from 0 to 8 here. And this is the statement in MATLAB that says, having evaluated the best fitting parameters, evaluate them along a whole array of points to be able to get a dense set of y's that I can plot a curve with. And here's what I got. I got these 5 values for the 5 best fitting parameters. And when I plotted it as a curve, I got the blue curve here that you see is some reasonable fit for the data points. Now you might be wondering what the red curve here is. I was telling you that you should ignore it. The red curve was the actual values of the b's that I secretly knew when I generated these 20 data points. So I've included that in the plot just so that you can get some idea in this example how close, with these 20 points and these sizes of errors that are shown by the error bars on each point, how close we get to reproducing the underlying curve, which of course is only secretly known to me. It's not really present in the data because the data is just a finite sample of 20 points. Now I want to draw attention here to B3 and B5. Do you see what those are? They are the amplitude and the width of the Gaussian lump in the middle of this model. Because later we're going to illustrate some other points by assuming that that's what we're really interested in. Suppose that in this data the dying exponential is just some artifact of the measuring apparatus, and what we're really interested in is the area under the lump here. And the area under the lump will be up to some geometrical factor of 1 over square root of pi or something. It'll basically be the width of the lump B5 times the height of the lump B3. Now let's ask a different question. We've obtained the best fitting parameters, b1 through b5, but how accurately do we know them? Or, as Bayesians, what we would say instead, what's the posterior distribution of the vector b? Because b is a random variable. B was a derived quantity from a set of random variables that were the individual error terms of the individual data points. So B itself has a posterior distribution. Now a way to estimate that is to take the Taylor series of the chi-squared function. Well, if we have any function that's a function of a vector b, in this case, the function is a half, chi minus a half times a function, so that minus a half is going to pull through here. We can write the Taylor series of any function of a vector around its maximum value in this form. Minus a half chi-squared of this vector b is equal to the value that it has at its minimum. And then the Taylor series in general would have a linear term, but that linear term vanishes at the maximum or minimum, as in this case. And then the next order term is the quadratic term. And for a vector function, the way that quadratic term comes in is there's a half that comes from the term in the Taylor series, from the 1 over 2 factorial. And then there are two vectors, one on each side, that are going to make a quadratic form, that are the distances from the b0 at which this minimum occurs. And then there's a second derivative of the function inside, and that is the matrix that sandwiches the vector transpose and the vector. So this is just the vector form of Taylor's theorem. Let's see if we understand where all the halves came from. One of these halves and the minus sign came from the fact that we're doing the Taylor series of minus a half chi-squared. And the other half came from the 1 over 2 factorial in the Taylor series itself. So before we just let MATLAB do the exploring of the chi-squared surface to find its minimum, but if we were doing that ourselves, we could also along the way calculate the Hessian matrix, that is to say, the second partial derivative matrix of the chi-square function. And in particular, we would want to know the Hessian matrix at the, I should say, b0 here, where the minimum occurs. Okay, then let's put this Taylor series into the formula for the posterior probability of b, which is simply proportional to e to the minus a half chi-squared. And e to the minus some constant is just some constant that I'll take out into the proportionality. And the part that's a function of b, or rather here b minus b0, is this term. And why have I written a sigma b inverse here? Well, what's really here is this matrix up here. And I'm going to define a matrix sigma b to be the inverse of exactly a half the Hessian matrix. And therefore, what goes in here is sigma b to the minus 1. Well, you can see where I'm going with this. Why did I define sigma b in this funny way? So that what appears in this exponential now has exactly the form of a multivariate normal distribution. So we've learned something. We've learned that if this Taylor series converges rapidly enough that I can just truncate it after the quadratic term, then the posterior probability of the parameters b here is multivariate normal Gaussian. And that's independent of did I have a lot of data points or a small number of data points. Well, it's not really independent of that, because if I have a lot of data points, it'll make this Taylor series converge very rapidly, and it'll be dominated like that. So this is actually a kind of a central limit theorem-ish result, but it's a very important result that when you do least squares parameter fitting, the parameters themselves will have a posterior distribution which is multivariate normal. Now, how do we actually calculate the Hessian? Well, MATLAB or Mathematica probably have routines, I haven't looked, that simply return the Hessian as part of the minimization of a fit. But if you ever have to calculate a Hessian, it's not difficult to do by finite difference. Let's just quickly sketch that. So the Hessian, the second derivative, let's suppose we want to take the second derivative of a function with respect to x and then y. So we're going to do each one separately by finite difference. First, here's the x and y plane. And we're going to go up here to this value of y. You'll see y in a second. And I'll compute the centered derivative of the function with respect to x up here. So I'm going to use the plus plus point and the minus plus point. And you can see plus plus minus minus plus, and then divided by their distance apart, 2h. So that's an estimate of the first derivative with respect to x up here. And this is exactly the same thing, but estimating the first derivative down here. And if I subtract these two first derivatives, and they're separated by a distance 2h, so I divide by 2h here, I get an estimate of the second derivative. Now if you pull these two h's out and take the minus sign through here, you'll see that you get this combination of the four corner points entering the estimate. And this is easy to code up in MATLAB. These were our previous best fitted values. This was the chi-square function, and this is just a tricky little coding of this formula up here. If you enjoy coding in MATLAB, you might see how I defined a unit vector in a way here that I didn't have to just do it by hand. There's also a little trick in this program that I'll leave to you to work out, that this works not only for x and y being distinct variables, but this will return the Hessian matrix also properly along the diagonal. And you'll have to work through the way these unit vectors work in the case that I is equal to j to see how that works. It's kind of a miracle that it works out, but it does. So back to our example. We were fitting this model to 20 data points. We got these values for the parameters b. We computed, with that code on the previous page, a Hessian matrix, which is a 5 by 5 matrix of second partial derivatives. And then we took the inverse matrix of 1/2 of the Hessian, and that's the covariance matrix for the parameters in the fit. Now sometimes the covariance matrix is just more information than you want. What you really just want to know is what are the standard errors, so-called, on each of these 5 parameters. In other words, here the parameter says it's 0.65, plus or minus what? And the standard errors of each parameter separately are the square roots of the variances. And the variances are these numbers that occur on the diagonal elements of the covariance matrix. So here I've calculated what the standard deviations are. I guess here they're called standard errors when you apply them to fitted parameters. The standard errors of the 5 parameters up there. Well, this all seems a little bit mysterious. Why are the standard errors of each parameter separately the diagonals of the covariance matrix? And what's the interpretation of these other elements? In particular, we're going to be interested, you'll recall, in B3 and B5. And that's what the red coloring is here. I've colored in red the 3, 5, in other words, 3, 3, 5, 5, 3, 5, and 5, 3 elements of the covariance matrix and the Hessian matrix. And we're going to see that when we're interested in something like the product of B3 and B5, we're going to have to know something about all 4 of these elements. But that's going to be in a future segment.